In this section, we'll begin our discussion of graphing in 3-space. But before that, we have to understand dimension of our domain and our graph. So let's talk about just the graph of the function and how many dimensions it is. If we remember from just algebra, hopefully you guys remember this, that how many dimensions would that be? Well, it's a line. So a line would be 2D. So this is in 2D. All right, so if I use that same logic, that's in 2 dimensions, then this is in 3. And we can tell really by the number of variables in our function, right? That's, we have an x and then we get a y. Here we get an x, a y, and then this is like our z. And then this one, I have x, y, and z, and then I also have the output h. So this is a 4D graph, whatever that may look like. We have no idea. I mean, we could try to graph it and create some kind of understanding, but we do know it's 4 dimensions when we graph it, whatever that looks like. All right, that's important, of course, to know the dimensions of your graph, but another thing to know is the dimensions of your domain. What can you plug in? How many dimensions will require you to plug in? So if we had to find the domain of this first one, let's use this as an example to understand this. I know that this has to be 0, greater than 0, can't even be 0, because I would be dividing by 0. That is a line, right? 0 to infinity. So the domain for this, domain is 1D. It's 1 dimension. I get one number that I got to figure out, right? That x can be between 0 and infinity. That's one number can be that. Here, the domain would be all x's and all y's. So this domain, we're not going to worry about trying to find it. It's all real numbers anyway. For x and y, so this is 2 dimensions. So our function has a domain of 2 dimensions, but the graph itself is 3, right? This one, the domain for this one, well, I'm plugging in 3 variables, so the domain is 3D, the graph is 4D. So you can see it's always one more, because we have the number of inputs, that's our domain, and then the output adds 1 to create a new dimension. All right, so we're going to discuss, we're just going to talk about what these look like. So discuss this function here. Okay, I have that. I'm plugging x, y, and z. So the domain is 3D. And the graph, so I would have x, y, z, and another output. So it is 4D. We're not going to graph it yet. We're going to do some graphs here in a moment. But all we're doing is discussing if the domain is 3D, 4D, whatever dimension. So we could graph this domain, which we're going to do in a moment. But to graph the actual function, the function is 4D. We can't graph it. But I can graph the domain and talk about it, which we're going to do. All right. A few more here. Find domain and range of that function. Okay, so it's a little bit more. I'm still going to write this out. Domain is, okay, I have an x and a y, so the domain is 2D, the function is 3D because the output is a z, and they want us to find the domain and range. So this is going to be the same thing it was back in algebra. I'm looking at different parts of my function, and I've just found, okay, I have a denominator there, and I know that denominators cannot be 0. So if I manipulate this equation, this tells me y cannot equal x. So my domain, that's the only thing. I can plug whatever I want into the top, right? I can times x and y. I can square y, and I can times it by x and times it by half. There are no numbers that I can't do that on. So the graph, the domain, we know it's 2D, so I got x and y. So that makes sense why it's 2D. So this is the set, that's what that means. The set of x, y such that, that's what the up and down bar means, x can't equal y. So all our domain would be any number x and y where x was not y, or y is not x, vice versa. The range in this, ranges are usually typically, are harder to find, but in this case, we can actually get anything we want out of this. I know it seems like we can't, but we actually could grab whatever we want. So we're going to say all z such that z is a real number. So we'll just put it like this. That's another notation, or you could say this, z is inside of, negative infinity to infinity. This means an element of. So you can use either one there. We're just describing domain and range. Why this is going to be important is if you notice in this problem here, the domain is a 2-dimensional graph, which means I can actually graph it. I can graph 3D too, but this is going to be like a projection of the numbers that I can actually plug in. All right, let's take a little more forward with another example. All right, domain and range of this function. Okay, so I have a square root that tells me that I got to avoid negatives out of there. It can be 0, it can be positive, just can't be negative. So all non-negative. So if I'm trying to find my domain, and I'm going to say what it can be. It can be greater than or equal to 0. All right, if I move things around, x squared plus y squared, so if I move it to the other side, I get x squared plus y squared is less than 9. All right, I also know that those are greater than 0, right, because they're squares being added together. So now I just write my domain. All domain, okay, so it'll be all xy such that x squared plus y squared is less than or equal to 9. We really don't need the 0 because it can be whatever. We're not going to get the negative out of that because they're squares. So that's the domain. Now the range, I got to think about, okay, I'm caught between 0 and 9. So I'm going to think about what I plug in. Okay, so if the biggest, what I'm saying inside of here, right, or let's even just look right here. This is 9 minus, if we think about it that way, maybe it'll help us out. So we have two options. I have a minimum, and that's 9 minus 9, which is 0. And then I have a maximum, which would be 9 minus 0 equals 9. So we're trying to find a range. Those are the insides that are going to be spit out, right? That's the max. Either I have between 0 and 9. I have that here. So I know that I get in between these two values based on that. Okay, so the range here is all z's such that z is caught between 0 and, okay, you got to be careful because this is going to go inside, so it's 3. Square root of 3, not 9. Or sorry, square root of 9, not just 9. There we go. So there's domain and range. The important part here, just like in algebra, remember we were always a little more focused here. The reason is because if we're creating models or you're creating machines, making machines in engineering, your inputs better be correct or you could really mess a machine up. For instance, one thing I always give an instance of for an example of in trig is when we're focusing on radians and degrees, if you don't specify which one your computer is going to do, there's a big difference between 5 pi, or let's even make it 2 pi, and 2 pi radians. Or 2 pi radians and 2 pi degrees. There's a big difference. If you would like to see a giant difference, take a number like 40 and do 40 degrees and compare that to 40 radians. Well, 40 degrees is not even in the first it's not out of the first quadrant, but I know that 2 pi is all the way around, which is about a 6. So this revolves like over 6 times, right? Because I can 6 times 6 is 36, so it's like 6 and then 2/3 of a time. Ish, right? Roundabout. So that's one example of why domain is important, because if the angle is what we're plugging in, we need to understand what we're plugging in so we don't destroy machines or even worse, take somebody's life.